So tomorrow we're going to climb up this fantastic mountain called exhumed, or which to the local paddlers is known as Old Baldy. So it's this magnificent inselberg, part of a larger granite batholith which forms the ancient granitic basement of the province, and it's going to be a fantastic day out. We're going to climb this mountain to look at a rock, an igneous rock, which forms part of the syllabus. You all have to study rocks and the rock cycle and the different rock types, igneous, metamorphic and sedimentary rocks. And tomorrow we are specifically going to look at these ancient granites, 1.1 billion year old granites that form this inselberg, which has been exhumed by the downcutting of the river. And so we're looking forward to going on that grand adventure and showing you these amazing things. Where we are going actually is a geomorphological hotspot, and there are these ancient granites and metamorphic rocks and igneous rocks, and it's all capped by wonderful sandstones, and we're going to look at the mineralogy and try and get some insights into the formation of granites. So that's on tomorrow's agenda, so looking forward to sharing that with you. If we haven't met before, my name's Gerald Davey. I head up Rock and Sky. So to make sure you don't miss out on this adventure and all the other adventures, please like, please subscribe, please click on that notification button. Visit us at www.rockandsky.net. We shall see you on the mountainside tomorrow.
So we're here on a grand adventure on a Sunday morning, which is a great way to spend a Sunday morning. So about 1.1 billion years ago, the world was a very different place from a geological point of view. There were three proto-continents, Atlantica, and Nina, and they collided with a larger proto-continent to create a supercontinent called And where those continents collided, mountain chains were thrown up. That collision zone, that suture zone, created a mountain chain which was bigger than the mountain chain that runs from the Pyrenees through to Burma, and including the Alps and the Himalayas. So we're standing in this place now, a collision zone between all these ancient continents. And where I'm standing used to be the root of an ancient mountain belt. And the reason why we came out today was to look at the granites and a granite dome called exhumed in the local Zulu language, or the paddlers and the canoeists who paddle past here, they call it Old Baldy. So as you might know or might not know from your plate tectonics courses, you get these collision zones where the continents or the plates meet, and you get subduction and you get partial melting of the crust, eventually total melting, and you get these granite batholiths forming, which rise up as diapirs in the Earth's crust. And what we're standing on now, this granite batholith, is one of those diapirs. So this is where I'm standing here, 1.1 billion year old granites, and I thought we'd come out today and have a look at it and show you this thing. So if you look down the valley where the camera is looking, you can see the granite stretching out in front of us, and the Umgeni River below. So there's another whole story with the Umgeni and the post-Gondwana downcutting. You'll know about the supercontinent of Gondwana, Pangaea, however you want to pronounce it. Where we are, Gondwana, the breakup at about 180 million years ago, that's where that started. And then the rivers had to make their dash down to the sea, and from the Great Escarpment about, oh, it must be a couple hundred kilometers from us here, so that's 3,000 meters down to sea level, which obviously is at zero. But that's another story. But this granite batholith has now been exhumed by the downcutting of the river, all these rivers that are making their way to the sea. So today we've come out to climb up this batholith, which I've been looking at for years now and thinking I need to get up on top of Old Baldy. So eventually my mate John, he'd been up here with some climbers, so he knew the way, and Alex, our famous cameraman,
We decided to come out and have some fun and climb up this huge rock. So it's a stiff climb, I promise you. But and we've been stuck behind the desk too long, getting fat and lazy. So I thought we'd get out and do some exercise and come for a walk. So I think you can see the view of the granites. We're going to try and fly the drone off here now if the wind isn't too strong, and you can see the granite faces. And then we'll take a close-up look at the crystals. Granite batholiths, because they are plutonic rocks, they take a long time to crystallize and to cool down, and then you get these large crystals forming in the rock mass. And that's very different to what happens when you get a lava pouring out on the planet's surface, and then they cool really rapidly and they're much finer grained. So we'll take a look at some of those. I can see them here, you can't see them just at the moment with the camera, but we'll take a look at some of those crystals which show that the granites have cooled over a long period of time. This all ties into the rock cycle and rock weathering, and I think sometimes the geography syllabus, you look individually at different aspects of it, but there's not like an integrated approach. So there's a whole plate tectonic story here where we're standing, albeit a 1.1 billion year old one. We're in an old collision zone, mountain chain that's been eroded away. There's the rock cycle involved here. Then we have to learn about igneous and metamorphic and sedimentary rocks. So as I stand here, we can go and look at some metamorphic rocks right from where we are. The sedimentary rocks forming here in the river as the sediments are being carried down towards the ocean. There's a whole fluvial dynamic story, fluvial geomorphology. So all these things are integrated, and we could go on a grand adventure around this valley of 1,000 hills and look at all of those things. But today I thought we're going to come out and look at the granites, because that's a specific part of the syllabus. When I say granites, I mean igneous rocks. So yeah, a granite is an igneous rock. There's a whole range of different rocks. Again, it's very simplified in the geography syllabus, and there's such a lovely story attached to igneous rocks. Chemistry, mineralogy, temperature and pressure, all those kinds of things. So that is a field of study in itself. You can spend years and years becoming an igneous petrologist. Doesn't that sound fantastic? An igneous petrologist. When you arrive at a party and you say, I'm an igneous petrologist, it's way better than saying I'm an accountant or a doctor or a lawyer. I promise you, everybody will come over and have the conversation with you, because you're the coolest guy or coolest girl in the room. You go blind in one eye, or your one eye goes to hell staring down a petrological microscope for months, years of your life. But that's a small price to pay to be such a clever person.
Better put my safety glasses on. Right, we've come around the side of the hill a couple of 100 meters, and we're looking out onto this absolutely magnificent landscape. I see granites on the other side of the river, and here's a nice granite outcrop that we are here to look at. So, as we mentioned earlier, the downcutting of the river has exhumed this massive granite batholith. So the granites have got essentially three minerals: quartz, feldspar and mica. So shortly we'll get Alex to come with a camera and we'll take a closer look at those minerals. Quartz is SiO2. Glass is essentially made up of quartz. It's that very light, glassy looking material. Feldspars are quite a complex mineralogy, and this granite is probably potassium feldspars and plagioclase feldspars, probably tending towards the potassium feldspar end of it. And then the biotite micas, which are very hard to explain. I have to show you a sample back in the laboratory when we get home. So I thought we'd just come and have a closer look at it, and we can see, because of once again we've spoken about this, because we're in the tectonic zone where the collision has taken place. We've got melting of the tectonic plates, we've got the formation of these diapers, like those lava lamps you get, those fantastic things where you get all this lovely colors rising up and as diapers in the lava lamp. It's the same thing here. We're getting this granite rising up in the crust. It's less dense, it's hot, and it intrudes its way towards the surface. And because it's at depth and the temperatures are maintained, huge crystals grow. And then we get this megacrystic granite, and we'll have a look at those crystals right now. That's compared to a volcanic lava which flows out on the surface and it cools really quickly. All right, so here we are in the exposed remnants of an ancient mountain chain and a granite diaper, a dome, a batholith. You're going to have to learn about those batholiths and laccoliths and lopoliths, which I'm not a huge fan of because I don't think you can't really see those things in real life. The only way you can ever see those kind of things is in a quarry. So I'm not very fond of that terminology, but the word batholith does sum things up fantastically well. So this is a granite batholith being exhumed. We could start calling it an inselberg maybe, or a Bornhard, and that's another topic in the geography syllabus. So when you read all those stories, those adventure stories, and they talk about the light glinting off the micas, that's a myth. The light actually glints off the feldspars, and you might be able to see it in the camera or not, but you'll see these shiny faces where they're angled optimally towards the sun. You can see the light shining off them. So those are the big feldspar crystals. These are big plagioclase crystals. I must get my head out of the light. So these are feldspars, these big megacrystic feldspars. And so because it's granite and it's cooling at depth and it's taking a very long time to cool, and there's time for the crystals to grow. So now we've got these formation of these feldspars. And then the lighter material that you see is quartz. And we'll look at a fresh piece of this. And then the black material is biotite mica. So those are, as we mentioned just now, the three major minerals that make up a granite. So we can have alkali feldspars, which are potassium rich, and then we get the plagioclase feldspars, which are calcium and sodium rich. So they're slightly different, but a granite's got a bit of both. Other rocks like granodiorites, those have more plagioclase feldspar than granites. But seeing we're on a granite batholith, which is why we are here, alkali feldspars, plagioclase feldspars, quartz and mica, and the mica being the black and the feldspars being these large crystals, and then the lighter, almost glassy, opaque glass is the quartz. Glass is essentially quartz, SiO2, and that's what the quartz is here, SiO2. Feldspars have got a very complex chemistry, which I don't want to get into at the moment. Well, I'll show you the chemical formula. We'll put it up in this video. Hard as nails, hard as granite. Granite is a very resistant rock. It can be metamorphosed, but it won't. It's always lighter than the basaltic material which makes up the ocean crust. And once it's made, it essentially floats because it's less dense than the more basic, the basic and ultra basic rock. So once it's created, it's here to stay. Very resistant to erosion. Where we are here, it's a more of a chemical weathering region than a mechanical, physical weathering region. So we can find rotten granites, but the granite can rot rather chemically rather than wear down physically. Okay, so if you want a tombstone made, granite's the thing, because it'll be here in 1,000 years. Whether your relatives come and visit you in 1,000 years' time or visit your grave is a different matter entirely. Alright, so I think we're done.